Hello, students. Welcome back to week 9 of the Signals and System NPTEL course. So, what I suggest is please refer to these sheets. I'm starting with this only. And today, obviously, the content is this Fourier analysis and LTI systems, week 9 content. So, this is me. Uh, weeks up to week 7 only I have uploaded. Let me upload till week. So week 9 content I'm uploading. Also, let me revisit this week 8. So this was week 8. Let me download. So people have asked me that I haven't uploaded week 8. So right now in front of you only I've uploaded week 8. Uh, so week 8. So just to confirm you had lot of doubts in week 8. So I can see people are not joining my class, but still they're asking me the questions. So in this Laplace transform circuit analysis, first of all, you had question on the ROC part, which I covered. Think which question you asked? Example 2 or something you asked, right? Example. Yes, yeah. So you asked here. So yes, I agree. Here I missed it is UT minus 1. Okay. So if you want to keep UT minus 1, you can keep. But by default, if you say, if suppose this UT is not there, okay, then in that case, the Laplace transform of e power 2t is not equals to 1 upon s minus 2. And ROC is also not equal to greater than 2. So basically, you want to keep this denominator greater than 0. Okay. So whatever value will be getting, you will be having that way. So if the real part, because S is nothing but sigma plus j omega. Okay. The sigma plus j omega, if it's sigma, the real part of S, which is sigma, if not it is greater, not greater than 2, then in that case it will become 0. Okay. Especially in the case of real part. And that is not feasible. Because for the system stability, Laplace transform is basically for the system stability. That's why we people are cared about this denominator not to be equal to 0. I hope that is clarified. But in case of Fourier transform, you don't have this type of situations. But you have some sort of Dirichlet condition that I covered in week 6, I guess. Okay, so you can refer the week 6 part. And also scaling property someone asked. Okay, so scaling property, uh, if what if you asked whether this is mod A or not? Okay, so yes, yes, it is not mod A, it is just A. So even if you search scaling property with Laplace transform. So it is, yes, it is not mod A. It's 1 by A only. I would like to show you some sort of MATLAB digital signal processing. I want to show some of the basic examples using this because as of now we have seen several questions and later I definitely have prepared a very good content on week 9. We will be going through that. But before that, let us go through some of the example concepts, sampling, and the use of this signal processing toolbox, specifically Fourier transform and Laplace transform. So let me Fourier transform. So these are some support that you can use. See, if you can copy this command and keep in the command window of the MATLAB, you can directly get this example or documentation completely. Okay, so I love MATLAB. Okay, so that's why I'm using MATLAB for your understand, for making you understand. But if you see my content week 1, week 2, week 3, I have used Python to show some sort of things. Okay, so as we know, and since the week 9 content is all about all about Fourier analysis and LTI systems. So that's why we'll be going through the periodic signals, Fourier series, and the system responses. And then some of the outline is like this: Fourier transform, periodic signals, then Fourier series representation, then Fourier series properties, then some properties of Fourier series that comes in part 2, then LTI system response or periodic input signal, uh, then yes. So my camera is switched on right now. Just I wanted to confirm this. So I hope you are able to see my screen. Okay. So yeah. So we will be going through the step of these process. Okay. Then Fourier series in continuous time examples. So Fourier series in continuous time examples. Continuous conclusion, wrap up, and wrap some extra slides that I have prepared. Then some of the questions and up to 8 questions that was covered in the last year that I have copied and with proper solutions. Okay, so I have prepared like this. So before this, what I would like to show you some of the deep concepts. Yeah. So let us first go through the whole transform of periodic signals overview. Then one by one, they will be going through the some properties with respect to MATLAB also. Okay. So periodic signals in time domain, and the frequency domain representation. Okay. So the relationship between Fourier series coefficients and the Fourier transform is what we will be seeing that. And the impulse, that is a direct delta, trains in frequency for periodic signals. And what is our key idea? So key idea is a periodic signal in the time domain refers to a discrete set of frequencies in the frequency domain, often represented by the impulses at the harmonics of fundamental frequency. Okay, so as we know, the periodic signal, which is a signal xt is periodic if it is repeating after certain time, and the time it's represented by capital T here. So xt plus capital T is equals to xt. That is, uh, can you give me my names for the periodic signals? What do you say? It's sine, cosine. Do you think that tan h is also periodic? It's a question mark for you. Okay, just let me know. And for some fundamental period t. So the fundamental frequency omega naught equals to 2 pi by t, and the Fourier transform of a periodic signal is, if xt is periodic, its Fourier transform x of omega consists of impulses separated by omega naught. Okay, the amplitude of each impulse is determined by the Fourier series coefficient. So what I am trying to say is, the Fourier transform we have seen so far. Okay, for your revision or for your better conceptual understanding, we'll go through the code. But yeah, but as of now, we have seen what is Fourier transform. Okay, but the specific case, if the input signal is periodic, in that case, a Fourier transform consists of impulses separated by omega naught. Or omega naught here is 2 pi by t. Okay. So as of now, let us see this. Okay, the Fourier transform is a mathematical formula that transforms a signal sampled in time or the space to the same signal sampled in temporal or spatial frequency. In signal processing, the Fourier transform can reveal important characteristics of a signal, namely its frequency components. Okay, so the Fourier transform is defined by the vector x with n uniformly sample points by y t plus 1, and simple, it is a discrete Fourier transform omega j k x j plus 1. Okay, so where omega is 2 pi I n is one of the n complex roots where of unity, where I is imaginary unit. For x and y, the indices j and k range from 0 to n minus 1. Okay, the FFT function in MATLAB uses the fast Fourier transform algorithm to compute the Fourier transform of theta. Consider a sinusoidal signal x, that is a function of time t with a frequency component 15 kilohertz, 15 hertz and 20 hertz. Use a time vector sample in increments of 1 by. So what is this? It's 1 by 50 over a period of 10 seconds. So 1 by 50 is actually T, a sampling period. Okay. So sampling is nothing but a switch. Suppose you are doing a switch, taking sample at 1, 2, 3, 4, 5, like this. Okay. So TS is nothing but 1 by 50, where T is equals to 0 to TS separated by 10 minus TS. Okay. Where X is nothing but sine 2 pi 15t sine to 2 by 20t, because we have signal of frequency sum of both components. So that we can write as a simple signal, that is a sine 2 by 15t. 2 pi is a common for that. 15 is one signal frequency and 20 is another signal frequency. And if we are plotting, so what if we are getting it like this? This is the amplitude, this is the time. What you are plotting is like the simple plot sample time with respect to the x. Okay. Compute the Fourier transform of the signal. So if we compute the Fourier transform, so let us compute this. And Fs is nothing but 1 by Ts. So what we are trying to do, we are writing F, which is 0 to length y minus 1 by, because we are plotting in terms of Fs at the frequency of Fs by length of s, y. Okay. So at every Fs we are plotting. So what can we write is, so create the vector f that corresponds to signal frequency space. Okay. So if we plot y f, then apps of s, that is a magnitude spectra. So this is magnitude with respect to frequency. This is what magnitude spectra and at the frequency of separated by Fs. So what it shows? The plot shows four frequency peaks. Although the signal is expected to have two frequency peaks, which is 15 hertz and 20 hertz, because our signal consists of two signals at 15 and 20 hertz, but still it consists of four peaks. What does this mean? Can you tell me what does this mean? And can you analyze what is this? What does this mean? Okay, so here, the second half of the plot is actually the mirror reflection of the first half. So you can see that you have, suppose you have 15 and you have 30. Okay, you have 15 and 30. That was supposed to be here. So what should be the 15 mirror plot? It can be. So what was that? 15 and 20. So sorry, 15 and 20. So 15 ka mirror is 30 and 20 ka mirror is, so 15 plus 15, you can say is 30. 20 plus somewhat mirror. Okay, if we divide it here. So 15, 20, and this is divided, and this is like looking like a mirror. So 20 plus somewhat 15 is again 35. So it's here 35. So in both the frequency components, you have two peaks. It is added with plus 15. Why it is added with plus 15? What do you think? What's the reason why only plus 15? So whatever frequency it will add, so that it will act as a reflection. That will be, I think, I hope my screen is visible. So please drop me a comment if my screen is not visible, okay? So the fifth, third, so okay, so what the components we exactly got? We got 30 and 35, okay. So discrete Fourier transform time domain signal has a periodic nature, with the first half of the spectrum is a positive frequencies and second half is a negative frequencies. But in practice, if you see the spectra that we draw, it's basically it's from the negative frequency domain, a negative bandwidth that we don't care, okay. But here we are seeing the first half is a positive, second half is a negative. Okay, the 10, 30 hertz and 35 hertz frequency combines the plot correspond to 20 hertz and 15 frequency, 15 frequency components. Okay, to better visualize this periodicity, you can use the 50 shift, which performs the zero shift circular shift. Suppose we have a 50 shift. If you have a 50 doing a 50 shift, you are getting proper spectra. So this is what I used to get it when you are doing it mathematically or through graphically. I hope this is clear. And yes, so n is a length of signal. So depending on the n by 2 to n by 2 minus 1, you are multiplying with fs by n. Why fs by n? Because fs is nothing but the sampling frequencies and that the n is by length. So you are multiplying with that. And y shift is equals to f50 shift of y, where we are plotting f shift, apps of y shift, and x level is frequency and y level is magnitude. So this is what about frequency domain. Okay. So there are some noisy signal computational efficiency. You can just check this. I'm not going that here because that was not related. I want here. So it is coming the same. You go to some examples. Just a second, I will reshare everything. So I would like to see some of the examples. So analyzing cyclical data such as an event in nature or period time. Yeah. So this is one of the example that is a periodic data. So analyzing a cyclical data with FFT. So you can use the Fourier transform to analyze the variations in data such as event in nature that is over a period time. So for almost 300 years, the astronomers have tabulated the number and size of sunspots using Zurich sunspot relative number. Plot the Zurich number over approximately the years from 1700 to 2000. Okay, 1700 to 2000. Take a closer look at cyclic nature of sunspot. So what does that mean? Uh, so the Fourier transform is fundamental to in linear process. It identifies the frequency components in data. Using a 50 function that take the Fourier transform of the Jury's data, remove the first element of the output which stores a sum of the data, plot the remainder output which contains the middle numbers of the complex Fourier constitutions over the real axis. See, the Fourier coefficients for why you are calculating Fourier coefficients here? That's what I would like to say. The Fourier coefficients is there for the cyclical data or the periodic signal. It's not for all. So this is Fourier coefficient, whereas Fourier coefficients are on their own are difficult to interpret it. A more meaningful measure of the coefficients is their magnitude square, which is a measure of the power. Since half of the coefficients are repeated in magnitude, you only need to compute the power on the first half, okay, or the one half. Plot the spectrum as a function of frequency measured in cycles per year. So this is what the power per cycles per year. And if you calculate maximum sunspot activity happens less frequently than once in per year. Just a second. You meanwhile you go through this. Okay, so fine. Sorry for the disturbance. So Fourier coefficients I was talking about. Okay. So if xt is a periodic signal, its Fourier transform consists of impulses separated by omega naught, and that we will be showing. Actually, this is cyclic data. This is different from the actual Fourier transform. But the Fourier coefficient is only calculated for periodic signal. Yes, let us see this. how can we get a square wave from the sine wave or vice versa? That is very interesting to note. So this example shows how Fourier series expansion for a square wave is made of sum of odd harmonics. That's where the concept of Fourier series comes into the picture. Okay, so if you say any periodic signal, any, okay, any periodic signal in the time domain is actually the sum of sine and cosine. And if we say particularly the case of square wave, so that square wave is actually made of sum of odd harmonics. So if we start by forming a time vector from 0 to 10 in steps of 0.1 and take the sign of all the inputs, plot this fundamental frequency. So we have 0 to 0.1 to 10 and sign of all the inputs. We have plotted like this. So this plot function just plotted here. Okay, next add the third harmonic to the fundamental frequency. Let's add some harmonic. Okay, so that is a 3t sine t plus sine 3t. Okay, why we are dividing by 3? Why we are dividing by 3? Because we are adding it here 3. Okay, let us add. Then plot is this. Now, now use the first and the third and the seventh harmonic. Okay, so sine t plus sine 3t by 3 plus sine 5t by 5 sine plus sine 7t by t 7 plus sine 9t by 9, and we are plotting it here. We are getting something like this. For a final for a final, go from the fundamental all the way to the 19th harmonic, creating a vector of successfully more harmonics. Okay, so I have written a program. Suppose, sorry, code is have written this program, saving all the intermediate steps as a row of matrix. Plot the vectors on the same graph figure to show the evolution of the square wave. Note that the Gibbs effect says it will never quite get it there. Okay, Gibbs effect. That's very strange. So T you are having 0 to 0.2 to 3.14. Then zeros, y is equals to zeros, 10 to length of t. X equals to 0 size of t. K is equals to 2 to 19, where x is equals to x plus sine kt by k. Y k plus 1 is x. Plotting y here, title the building of square wave, that is Gibbs effect. Okay. So this is what it is showing. So 19, you're having like this. Previously it started from the 1 sine t, then sine 3t by 3, then sine 5t by 5, you are having 1 of building. And here is a 3D surface representing a gradual transformation of sine wave into a square wave. See, like this. This is very interesting to note. Now I would like to ask you, think about it. Can we get a triangular wave from starting from the sine wave or the cosine wave? Just check and let me know. Try to find a program or trying to think from your mind. I don't know. I don't know whether my mic was off or on by this time. But yes, I was explaining you with the different topics and some deep questions. So the deep question number one was prove that if xt has a period t, then xt minus T naught has a sample period t. Show that this fact aligns with the time shifting properties of Fourier series coefficient. So Fourier series coefficient, so far we have seen that using Fourier series coefficient, we can just write the time domain signal or the periodic time domain signal. Remember this periodic time domain signal in the sum of sine and cosine, and that we also saw using MATLAB. Okay. But we had some doubt here. The Fourier series is actually the series representation of periodic function in terms of sine and cosines. So that you can write in the form of and sine. Sorry, the square wave function was simple. The sum of sine t plus sine 3t by 3 plus sine 5t by 5 like that. Okay. Similarly, I asked you to solve for the triangular signal. Okay. Now let us prove this. So how will we prove? So if we just check the periodicity, so we'll have xt plus capital T is equals to xt as we know. So we can just write xt minus t naught plus capital T is equals to xt minus t naught. So that is also having a period t. Okay. Now Fourier series coefficients. So the shift introduces a factor which is equals to e power minus j k omega naught t naught. Okay. But does not alter the fundamental period or omega naught. So, which conclude that shifting a periodic signal does not change its period, only phases its harmonics. Okay, so that's what our concern was. Show that these facts align with the time shift properties of Fourier series coefficients. S- So we have seen all these functions. I am just repeating. I wanted to show you this. Yeah, so I wanted to show you that for the even signal, we have this, okay. Similarly, which leads to this is the Fourier series coefficient, okay. If we replace with minus k, it is giving the conjugate symmetry. So it is having for the even signal. Whereas if you remember uh in case of Fourier transform, what you had? You had Fourier transform. Okay. You had Fourier transform and you have to replace j with minus j and it was giving you f of j conjugate. That is for the even signal. Means you will only have the real part. You were having the imaginary part as zero. Similarly, if you relate with the Fourier series, so here also for the even signal specifically, the imaginary part often cancels out and making ck real. So that was a real, a purely imaginary in case of odd signal. Okay, purely imaginary in case of odd signal. Odd signal means xt is equals to x of minus t. Now we saw this. Okay, I want to show some of the more detailed properties of Fourier series, which are Parseval's energy theorem, convolution in time, and differentiation integration in time domain. So Parseval's this can be written in the form of energy or power. So if we say power, so if you have having a periodic signal, then it will be having a Parseval's power theorem. If you are having non-periodic signal, then you will be having Parseval's energy theorem. So non-periodic in that case is um, non-periodic means definitely it's repeating in time or it is periodic in nature. So you have to calculate the power over one time period and you have to average it. Whereas for the energy signal, it is indefinite, like it is defined for indefinite number of time, but at the same time it is not repeating. So you have to integrate over all the time period. Okay, that I have really covered long back. So yes. So this is Parseval's theorem. This is what it is, Parseval's theorem. Let me Let me keep on charging. And meanwhile, you go through this. So this is what it's what power or energy? It's power. It's power. Okay, why? Because it is averaged over one time period and it is returned the sum of that. So it is power. And if you say it's what's the proof of that, so we'll calculate the proof as well. So it's integration over T naught, say T naught plus T, and it average over 1 by T, and it goes to summation of minus infinity to infinity mod of Ck square. So the energy of the signal, it's power, so it's my mistake. So energy of the signal and so power of the signal in time domain is equals to sum of the square of magnitude of Fourier series coefficients and useful for power energy computation. So anytime you can replace with energy and power. So one more tricky thing in our mind. So since we cannot define the Fourier series for a non-periodic signal, so it's always be power, not energy. So my mistake here. I didn't prepare well. Sorry. You can just. It takes a lot of time, so maybe I have done some sort of mistake. I'm sorry for that. So time domain convolution, if you say, so it's just a very interesting point to note that if you have time domain convolution, x1t convolution with x2t and where and x1 and x2 are periodic with period t, then the dk are the Fourier coefficients of yt, which is a convolution of xt and y, x1t and x2t. That is basically the multiplication of the Fourier series coefficient of individual series. Okay, it's like that. If you want to see the implication, the convolution in time domain correspond to pointwise multiplication of Fourier series coefficients. So it is a differentiation in time domain, and the result is new Fourier coefficients are just multiplication of j omega naught ck. So I would like for you to understand what was the case for the Fourier transform. I want from you. Just give me a second. I will keep the charger. Hmm. I hope my screen is visible. If not, please let me know. So I think Chaitanya Lakshmi. Can you hear me? Hi, Chaitanya. Yeah. So have did you register for the exam, Chaitanya? Hello. Did you register for the exam?
No, no.
Acha, so you are just attending for your knowledge. Okay. So yes. So you are having this Fourier series coefficients for j k omega naught multiplied by ck. And there are some questions which I have prepared that involves the proper reasoning. So suppose you have question as using Pascal theorem, prove that the energy of a periodic signal. So what do you think that energy of the periodic signal is what? It's infinity. Okay. Energy of the periodic signal is infinity. Signal OT over a time is the same as sum of the energy of their harmonic. It's illustrated with an example. So let's see. So in practice, it is infinity. So let us see our proof outline. So Pascal's energy theorem says that like this. Okay, we have this expression. Now, my concern is you're having each CK mod square can be interpreted as the energy contribution because of the kth harmonic, isn't it? Why that is the case? Because you're having a Fourier series as sum of sine and cosine. So one sine and cosine is leading to one harmonic. So their Fourier series coefficient is leading to the energy contribution to the harmonic. Why energy we are talking about? Because since it is it's a square of that, so it is a energy contribution. So for a square wave Fourier series coefficient, example Ck is 1 by k, because we saw that square waves can be written as since square is actually the odd signal, so it's a sum of sine t plus sine t by 3 plus odd harmonics. So sine plus sine phi t by 5 plus sine 7t by 7 for odd k. Summing, so what that is, you are having Ck as 1 by k. Okay, because that one k is leading to odd one. Okay, so 1, 3, 5, 7, like that. So that is summing 1 by k square over odd k gives a total finite energy in one period. So that is true. Okay. So this is the interpretation that I told. Now we will be going through the proof. As we know, if we convolve in the time domain, that is a circular convolution over one period. Why it is circular? Because we are convolving this x1 to x2 to as a periodic signal. Both are periodic in nature, so it's a circular convolution. Circular means periodic. Okay. So then shows the Fourier series coefficient of yt as in multiplication of this. See the steps. So x1t can be written as summation of k is equals to minus infinity to infinity ck power 1 e power j k omega naught t, and similarly for x to t. So convolution y t can be written as minus infinity to infinity x1 t x to t minus tau d tau. Okay, but over one period for a periodic signal, since it is a formula, by the formula. And if we are having each exponential term in x1, so this is x1, and multiplies each exponential term in x2, so leading to pointwise multiplication of corresponding coefficients. So thus, this dk is equals to ck1 and ck2. That's very simple and straightforward. So if we move forward to the LTI response of the periodic inputs, how it behaves. So if you see a periodic signal, if xt is periodic signal, and system is also LTI, as we know, the output is also a periodic signal with the same fundamental frequency, assuming bipo. The reasoning, because each harmonic of xt is scaled by the system's frequency response at that harmonic. So that's very interesting to note actually. If xt is periodic, then yt is also periodic with the same fundamental frequency. Means if the sine is the input signal, so and irrespective of what ht is, we are having the yt is periodic with same fundamental frequency. So mathematical formulation is, if you can write xt as a summation of minus infinity to infinity ck e power j 2 pi 9% charge. Okay. Ck e power j k omega naught t, and system transfer function if you just multiply and just convert. So what is this? It's multiplication. The output Fourier series is ck h j k omega naught, because this is multiplication with j k omega naught, and that is giving you the Fourier series coefficient for uh, h of j omega. So physically, if we see what is the interpretation, so imagine a system you're having input output and the simplest response. So each harmonic of xt is treated independently by the LTI system, where the amplitude scaling will be happening through mod of because ck is multiplied by e h j k omega naught. So the amplitude scaling is by mod of hk omega naught, where the phase shifting is phase of hk j omega naught. So output YT has the same fundamental period but different harmonics or amplitude of phases. This is one example that you can see and look forward if you don't understand this like no. Okay. So suppose xt has a Fourier series coefficient ck so that the output of an LTI system with impulse response h of j omega has Fourier series coefficient again multiplied by this provide a formal convolution based argument. Okay. So this is what the convolution based argument. Since yt can be represented as xt convolution with ht, and if you say what and it can be written as x of tau. So since x of tau it's again a periodic signal, so this can be represented as term of Fourier series. Okay, so this is represented Fourier series. If you put this to be here, this in this above equation. So convolution with h of t minus tau translates to multiplication by h of capital H of j k omega naught in the frequency domain. Summing up all the harmonic yields yt is equals to summation of ck capital H j k omega naught into e power j k omega naught t. This is what it is giving. So question is, how does the phase response of LTI system affect the waveform shape of the output for a periodic input? Is it possible for phase shifts to cause significant distortion? I want you to first explore this and just coming for a water. Okay, I'm giving you the solution also. Just try to get through that. So, my intention to say you that there's a difference between minimum phase and linear phase. So, a linear phase system, what is that? It preserves the relative phase between harmonics, reducing distortion. So here is what it's showing the linear phase, okay? Because the overall harmonics is sum of the shifted harmonics. Large phase variation across the frequency can distort the wave shape. We will tackle typical signals, full wave rectified signal, half wave rectified signal. Suppose you have xt as mod of sine omega naught t, period is 2 pi by omega naught. Whereas Fourier series coefficients is real value, typical primarily, even harmonics integration can be performed piecewise over one period. So symmetry can simplify the integral. So this is what CK is. So what do you think? It's odd signal or even? Any idea? It's odd. Okay, sine omega naught t is there. Typically results in signals with only cosine terms for real signals. So this is what cosine terms for the real signal. If it is odd signal, then you're having, sorry, imaginary setting, then you will be having the odd part. I'll give you some. Hmm. So if we derive the Fourier series coefficient for the full wave rectifier, then identify which harmonics are present and which vanish. So you're having a solution to D question number 1, sketch. So since you have period this, it's very simple. So I think rectifiers and all are in touch, so I'm just leaving it. The pulse chain is very important. So if you have periodic signal of rectangular pulses, then Fourier series coefficients have this known form. I want you to remember this. So this Fourier series coefficient. So prove that a triangular wave's Fs Fourier series coefficients decays on the order of 1 by k square. Explain why this implies a smoother waveform compared to a square wave which decays like 1 by k. So I want solution from you. Just give me some seconds. I will just bring water and again join. Try to solve this. So reasoning is this. And I want closed form equation from you. So far, we have seen lot of questions, lot of deep questions, lot of concepts. So what I'm suggesting, let's just go directly uh to last year questions and their solutions. So I'm just going. So question number 8. Okay. So determine the Fourier series coefficient AK for the signal YT, where 1 is just a triangular signal from 0 to t. So where the signal is periodically repeated, the accepted result is AK is equals to sine k omega naught t1 by k pi. So I will show you the steps. It takes a lot of time in preparation of this material. So just go through this. So if we define omega naught is equals to 2 pi by t, Fourier series coefficient is AK is 1 by t, 0 to t, yt e power minus k jk omega naught t dt. Because yt is equals to 1 from this, so ak is nothing but this one, and it is by integrating we are having these values. So rewrite using Euler's formula. So if we write this, okay, and if we get like this, simplifying the magnitude is this one's, and it matches sync like form because if t and t1 are such that omega naught t1 is equals to pi, for example, if we get ak is equals to sine k pi by k pi, or generally ak is equals to sine k omega naught t1 by k pi. Okay, so moving to question number 7. The Fourier series representation is defined for answer is periodic signal. Step by step is like this only. It's specifically the expansion of periodic signal into sums of harmonics. For a periodic signal, we use Fourier transform instead, not a discrete sum of harmonics, and only correct option is periodic. Okay, and oh yeah, Pascal's theorem is used to measure what is what, and the resultant value for the periodic signal gives simply the option number A. And if you want the step-by-step derivation, you can just have this. Because using the Pascal's energy theorem, we have this one. And interpretation, it relates the signal's energy in the time domain to the sum of squared of magnitude of Fourier coefficients. And hence, it measures the energy of periodic signal. So energy is this one. And energy of periodic signal is often represented as power of energy periodic signal. So don't worry about that. Okay. So question number 5 is, if a real periodic signal xt has a Fourier series coefficient k ak, and what is a of minus pi? What do you think? A real signal. So it will be only 2 minus 3j. Why? Because it is a Fourier. It's a it's only the value with conjugate. So it's 2 or minus 3j. Very nice. Okay. So I'll give you some time. Just take care. Determine the Fourier series coefficient of a of minus 1. For xt is equals to sine of 3t. So I have given a hint also. Think about the fundamental period or do the direct computation here. Think about that. What will be the a of minus 1? How will you calculate a of minus 1? This was a question from the last year. How to compute? So I will show you the steps. Laptop is hanged up. So fundamental frequency has the sine of 3t has period t is equals to 2 pi by 3, where omega naught is equals to 3. So writing sine t in exponential forms, okay, matching with the standard Fourier series coefficient form. So if you're matching, you're getting like, because if you write in the Euler form, this is exponential form, is a Euler form only. And if you're writing and matching with the standard form, you're getting like this. But just by the comparing, you're getting A1 is equals to 1 upon 2j. So A of minus j is equals to 1 upon minus 2j. So it was the optional question. So options are given. Now, question number 3. Quick, quick, quick. So if a periodic signal xt has a Fourier series coefficients ek, what are the Fourier series coefficients for the even component? X of et. What do you think? Even component. It will just a sum of signs. That too even part of signs. So let me show you the solutions step by step. So you have to write in the definition of the in part, express like this, xt and x of minus t in terms of their Fourier series coefficients. And step 3 is add them and factor out the exponential. So if you are factor out, so you are getting 2 cos k omega naught t. So x of et is equals to minus infinity to infinity ak cos k omega naught t. In the complex exponential form, the coefficient in front of e power j omega naught t becomes like this, ak plus a of minus k by 2, where the new coefficients are ak power of e is equals to ak plus a of minus k by 2. Question number 2. Tell me the answer. So for a two arbitrary periodic signals xt and xyt with periods t1 and t2 and the Fourier series coefficients ak and bk respectively. The Fourier series coefficients for 4 of xt plus 3 of yt are. What do you think? So my answer is 4 ak plus 3 bk if t1 by t2 are integer. Okay. Not integer, sorry, rational number. Let us see their solution. So understand the superposition of two periodic signals. It is having the meaningful set, a single set of Fourier series coefficients only if xt and yt share the same fundamental period or the integer multiples of each other. The same fundamental period is not needed, okay? Because t1 not equal to t2, that the combined signal may not be purely periodic with a single fundamental frequency period unless the one period divides exactly by other. So in practice, the simplest addition is if it holds. So the correct option is this. So what I assumed is if T1 by T2, if T1 by T2 is simply if T1 by T2 is simply a rational number, in that case it can be added. But it cannot be added because you cannot make sure whether it is periodic or not. So T1 should be equal to T2. It's very much good analysis that I have done so far. So just to confuse you, I gave you wrong answer. Yeah. Let's go to the basic first question. So if a periodic continuous time signal with a fundamental frequency omega naught and the frequency Fourier series coefficients ak is input to LTI system with frequency response h of j omega, the Fourier series coefficient for the output will be, we know all. So it's ak multiplication with second option. No, third option. AK multiplication of h of jk omega naught. So for your step, I have written step 1, step 2, step 4. So understand this. Understand this first. So check my solutions, like how I have made for you. It's always step by step. If you can think that way, then only you can realize that how you are doing. Otherwise, at some point of time, you will forget. So moving to some sort of questions and analysis. So since time is left, so I'm going through that. And in between, if my class was not hearable to you, you should have told me because I was teaching only, and still it is not. Then there's some issue with this Teams. So I kept it open, but I couldn't. So I was clicking on this mute unmute button, but it to me it showed it's unmuted, but for you I think it didn't show. I was just checking the recording, so I'm so sorry for that. But yeah, the PDF will be uploaded for you for your guidance. So some sort of you can see the slides. It's properly defined. So what my analogy is, you go through these slides, prepare your questions, come to me. I will explain you everything. So, okay, if no further questions, I will stop the recording and you can definitely reach out to me. Thank you so much for joining, and I'm stopping the record. And so for you, let's meet in the next class. And yeah, so as of now, saw some of the um, mails about the doubts. So I have covered in the class. So those who are not able to join online, they can just check my YouTube channel and check. At least you can check my the content. Thank you.